Okay, in the last video we discussed linear programming, and specifically we talked about how to deal with inequality constraints using slack variables. So in this video we'll pull it all together into the simplex method. We have basically all the underlying conceptual, intuitive understanding of the method, and the simplex method just pulls it all together into a coherent whole. And it's a bit more algorithmic, although I'm not going to give a lot of the details in terms of really digging into how you would actually program a simplex method, because that's not the objective here. I just want you to understand how it's set up and how the process proceeds to find the optimal point. All right, so let's talk about the simplex method. And remember from last time we talked about the standard problem. So we have the objective function j, which is the inner product of c with x, or which is the same as c transpose times x. X is the vector of design variables, x1 through xn, so there's capital N of those. And then the c vector is the coefficients of the design variables in the objective function. Then we have the equality constraints, which are in the form of a matrix, ax equals b. There are m plus s. So there are n, capital N, so Nancy design variables. There are m equality constraints and s inequality constraints. So once we use the slack variables to convert the inequality into equality constraints, we have m plus s of these, and that's the size of this ax equals b matrix problem. And then we have the positivity constraints. So there are, again, n original design variables, now s additional slack variables, each of which have a positivity constraint that they must be non-negative. All of the variables, design variables plus the slack variables, get incorporated into a single vector x, and then the size of A, if you track all those sizes, the size of the matrix A is m plus s by n plus s, and the right-hand side vector is m plus s by 1. So again, if you track all those through, you'll see that the sizes all match up. So then the simplex method takes advantage of the fact that when we're doing linear programming, our linear function, subject to its linear constraints, the optimal point, the point that we're looking for, is one of the corner points of the feasible space. So remember that the feasible space is the region in the design space, so all of the x1 through xn variables. It's the region in that space that satisfies all of the constraints. So that's the feasible space. And then one of the infinity of points in the feasible space is the optimal point. And that is the point that we're looking for. And remember from our discussion last time, the optimal point has to be at one of the corners of the feasible space. You can remember those feasible space diagrams we had from last time. So again, we have the feasible space, and now we're going to introduce the basic feasible solutions. I warned you that there are a lot of there's a lot of jargon here, a lot of terminology that we have to be aware of, which of course is annoying, but you'll get used to it. So again, feasible space satisfies all of the constraints. The basic feasible solutions are all of the vertices, the corner points of the feasible space. So those you can think of as candidate optimal solutions. And it's the one that we're looking for that gives us the smallest value of the objective function. So we illustrated for our train car example last time, we had two possible solutions. Our basic feasible solution, the feasible space, remember, was a straight line. And the basic feasible solutions were the two ends of that line segment. And then one of those two ended up being the optimal solution, the one that had the smallest value of the objective function. So again, all that carries over into the general simplex method. Now, because the minimum occurs at one of the corners, we could just simply evaluate every corner point, determine the corresponding value of j, and then select the one that has the smallest value of j. That's essentially what we did in the train car example. Problem is, in that example, we only had two possible basic feasible solutions. but these can get very large very quickly. So as an example, if you had n plus s variables, again, n is the original number of design variables, s is the number of slack variables that we introduced, and m plus s equality constraints, again, m is the original number of quality constraints, and now we have s additional equality constraints that were converted using slack variables from inequality constraints. So n plus s variables, m plus s equality constraints. So if you just do the basic calculation to determine how many basic feasible solutions there are, so basically how many corners are there in the polygon, you get this number. So it's n plus s factorial over m plus s factorial times n minus m factorial. Now, that's not very meaningful, but let's just take an example where n is 20, so 20 design variables. We have 5 equality constraints and 5 inequality constraints. So if you put these numbers into this relationship, because of the factorials, remember how those work, you end up getting 3.2 million basic feasible solutions. So, and that's not even a very large problem. That's only 20 design variables. So you can see how quickly these grow. So just searching through all of the basic feasible solutions and calculating J and finding the one that has the smallest value is not very IT engineering like. So it's unnecessarily tedious and would take a great deal of time. So we'd like a better strategy for searching through. So what the simplex method does is then it defines a step-by-step procedure whereby we'll start with one of the basic feasible solutions, so one of the corners, and then we'll go from corner to corner in such a way as to, every time we do that, reduce the value of j, and therefore find the optimal solution without having to search all 3.2 million points as in the previous case. All right, so to do that, we set up the simplex tableau. Tableau is just a fancy French sounding word for table, and it's an augmented matrix. So you'll notice here we have A times X is equal to B. So those are clearly the equality constraints. And then we also have 1 times J from the first row, 1 times J plus minus C transpose times X is equal to 0. So that is, of course, then the objective function. So the simplex tableau includes the objective function in the first row, and the subsequent rows take care of the constraints. But they put them all together into one matrix problem. Now this 1, you'll notice, is not bold. That's a scalar 1. This 0 is bold, so that's a vector 0. And this 0 is not bold, so it is a scalar 0. J is a scalar, X is a vector. And we'll go through all the sizes of those, and you'll see that they make sense. This is what's called a block matrix. So each of the blocks, there's 4 blocks, but each of the blocks could be a vector or a matrix of an appropriate size that forms a much larger matrix. So again, as I said, the first row is 1 times J minus C transpose times X is equal to 0. So that is simply the objective function that we had before. And then the remaining equations are the constraints that we had, ax equals b constraints. All right, so here are the sizes. So the vector c is the coefficients in the objective function. There are n original design variables, and now s additional slack variables. Now remember, the slack variables all have 0 coefficients because they do not enter into the objective function. So while there are n plus n elements in the vector c, s of those elements are 0. So they're included because now we're going to include in x all of the slack variables as well as the original design variables. Then A is m plus s by n plus s. Once again, we can go back. We already discussed that size, and you can convince yourself that that's correct. And then B is m plus s by 1. So it's a vector, column vector, m plus s by 1. All right, now I already discussed this, the zeros. There's a scalar 0 and the vector 0 in there. And then, so when we put this all together, our simplex tableau, it has m plus s plus 1 equations for n plus s plus 1 variables. So let's just walk through that. So the equations, the m equations come from the original equality constraints. The s equations come from the original inequality constraints, which have been converted into equality constraints, which are now part of A. And the 1 comes from the objective function, which is that first row of the equation. The number of variables is n plus s plus 1. The n is the original design variables, plus the slack variables that we've introduced, plus j. So that's the 1. Now remember, n is always bigger than m. So the number of design variables is always bigger than the number of equality constraints in the original problem. Otherwise, we wouldn't have an optimization problem at all. So in the train car example that we discussed last time, so if you go back, I won't go back here in the slides, but if you go back and look at equations 6, 24, 25, and 26, we have the objective function, we have the constraints. Those are all now included into this simplex tableau. So remember, the first row is the objective function. So let's walk through that. So there's 1 times j minus 10 times x1 minus 15 times x2, and then 0 and 0 times s1 and s2, and that's equal to 0. So that is, if you go back and look, that is the objective function, just where everything has been pulled over to one side of the equation. And then we have the second row is 0 times j. Notice all these are zeros, so all of the constraints, that's our 0 vector that we had before in the general form. So it's 0 times j plus 1 times x1 plus 1 times x2 plus 0 and 0 times s1 and s2 is equal to 100. So you'll remember that means x1 plus x2 is equal to 100. That's the total number of cars that we need to transport with the two trains. That was the original equality constraint. And then we had two inequality constraints that said that the first train car could only pull no more than 50, and the second train engine could pull no more than 75 cars. So the first of those is 1 times x1 plus 1 times s1. So x1 plus s1 is equal to 50. So remember, x1 was less than or equal to 50. We add the slack variable. So x1 plus s1 is now equal to 50. So that s1 takes up the slack. Whatever amount less than 50 x1 is, s1 takes up that slack. Then in the final equation, we have 1 times x2 plus 1 times s2 is equal to 75. Same idea. So x2 has to be less than or equal to 75, and we can turn that into an equality constraint by adding the slack variable that takes up the slack for the second train. All right, so we put together all of the equations required to be satisfied in our simplex tableau for this particular optimization problem. So it's now a system of equations that includes all of those things. Now we can also write this in a little bit tamer looking form. So rather than as a matrix problem, we can write it in this tabular form. It's the same information, it's just a table instead of a matrix. So here you have the list of variables j, x1, x2, s1, s2, and then the right-hand side b vector. And then you have for each equation 1, 2, 3, 4, corresponding to these 1, 2, 3, 4, you have the coefficient for j, x1, x2, s1, s2, and then the corresponding b vector. So again, it's the same information, it's just in a little bit different form. And one thing you'll notice, whichever form you look at, there's lots of zeros. So there's lots of zeros in here. And remember, when we have a matrix with lots of zeros, we say that it is sparse. And it gets even more sparse as it gets larger. So that's good. That makes it easier to solve when we look at how we actually solve it. Now, these are some guiding principles. This is not a strict algorithm. So we've discussed, detailed algorithms such as Gauss-Seidel and LU decomposition and so on. We go into great detail, the steps that you follow to do the process and complete the algorithm. Here, I'm just going to give you a set of guiding principles. So these are things that guide the process, but not to the level of a programmable algorithm. All right, so the first guiding principle is that because the optimal solution occurs at one of its corners, one of the corners of the feasible space, the values of n plus s minus m plus s, of course the s is canceled, so that's n minus m of the design variables and or the slack variables must be 0 for the final optimal solution. So if you can think about that, if you go back to the train car example, you can work your way through and determine that that is the case. And we'll do that example in a moment and see how that works out. But anyway, so we know ahead of time for the final optimal solution how many of our variables, both from the original design variables as well as from the slack variables, we know how many of them must be 0. We just don't know which ones. So, for example, if there are 3 more variables than equations, so n minus m is 3, then we would have 3 of the variables that have to be 0. Okay, so that tells us how many of them are 0. So in other words, they're at their positivity constraint. So all of them have to satisfy the positivity constraint. This criteria tells us how many of them are actually at the positivity constraint and actually equal to 0. Now, more jargon. So the subset of variables, design and slack variables that are 0 are called the non-basic variables. And then the remaining ones, which are non-zero, are called the basic variables. So this is a little bit confusing. The way I remember it is the ones that are 0, those are non-basic variables that has the O in it. It's like a 0 in the non. So non-basic variables are 0 and basic variables are non-zero. And again, now our task is to figure out at the optimal point which of the variables are non-basic and which of them are basic. And essentially that's what the simplex method is doing. It's a step-by-step process for determining which of the variables fit into each of these 2 subsets of variables. And we know how many are in the non-basic as well as the basic variable set. It's just a matter of now determining which ones go into each. Now with the non-basic variables, those are the ones that are 0, a unique solution does occur, and that is the one that minimizes the objective function. So that's what we're trying to find, and you'll see how that works out in an example. All right, so let's look at our train car example. Again, in standard form, that was equation 632. You can look back at that. We just wrote, that was just a couple slides ago. So this was the simplex tableau of the train car example, exactly like we had before. So again, first row is the objective function. Rows 2, 3, and 4 are the ax equals b. So that's the constraints, the equality constraints. Now in this case, n is the number of original variables, which was 2, x1 and x2. M is the number of equality constraints, which is 1. The original equality constraint is the second row. So n minus m is just 1. 2 minus 1 is 1. So that means that one of the variables will be in the non-basic set. That's the one that will be 0. And the other 4 variables, because there's 1, 2, 3, 4, 5 variables now, the other 4 variables will be non-zero and therefore in the basic set. So 4 non-zero in the basic set, 1, 0 in the non-basic set. Once again, we just don't know. Is it x1, x2, s1, or s2? That is the one that is going to be 0. So we just have to determine that. That's our job. I say simply, obviously, for a large problem, it's not going to be so simple. But one of the design variables or slack variables will be 0 and therefore in the non-basic set. Now remember from the train car example, there was only 2 possible points. So the basic feasible solution was either point A or point B. So we only have 2 possibilities here. So let's just walk through each of those 2 and show how the simplex tableau is going to work out. So point A corresponds to, if you look back, where S2 is equal to 0, and point B corresponds to when S1 is equal to 0. So if we look at point A, where S2 is equal to 0, what we can do is take our simplex tableau, the matrix form, and extract out the variable that is 0. So that's the one that's in the non-basic set. So for point A, it's S2 that's equal to 0. So S2 is a non-basic variable, and we're going to pull that and its coefficients out of the rest of the problem, and you'll see exactly what that does for us. Because if you look back, this is 1, 2, 3, 4 equations for 1, 2, 3, 4, 5 unknowns, the number of variables. So it's 4 by 5, so it's underdetermined. We discussed that last time. So we have an underdetermined system of equations, but if we take out the one non-basic variable and its coefficients, then we end up with a 4 by 4 system of equations to solve, which has a unique solution that we can then obtain the j, the x1, x2, and s1. So here's how it goes. So if you go back and look, here we go. So we're going to take out the S2. So for point A, that corresponds to when S2 is equal to 0. So to take out S2, we have to take that out along with the coefficients, which is the last column in our matrix that's multiplied by S2. And then we'll leave everything else. So what's left, the first, second, third, and fourth columns of our matrix plus the fifth column times S2. But S2 is 0. So therefore this is gone, and now we have a 4 by 4 system of equations. So four equations for 4 unknowns. And then we can solve that. So if you write that out in matrix form, we can divide A into AB and AN, X into XB and XN. The B stands for basic variables, N stands for the non-basic variables, the ones that are 0. So the XN here is S2, and the AN is the last column of A. And then A, B, and XB are everything that's left. Okay, so if A, B times XB is equal to B, because the the XN are 0, so therefore this is our system of equations. It now, as I said, is 4 equations for 4 unknowns, so it does have a unique solution. And here is that unique solution. You can get it by taking the inverse of A or any of the other techniques for solving a system of linear algebraic equations. And then we get J. J is the value of the objective function. We get x1 and x2. That's the number of train cars on each train. And then we also get the value of s1, which is the slack variable corresponding to x1. All right, so you get 1375 for J, and that's what we'll compare to point B. This corresponds to 25 cars on the first train and 75 cars on the second train. Then we do point B. So point B corresponds to when S1 is equal to 0. So now we go back here. We're going to take out the S1 variable, which is the second to last one. So the coefficients of that will be the second to last column in the matrix. And then everything else will be what's left. So here is the 4 by 4 matrix. When you take out the second to last column, then that's J, X1, X2, S2. And we've taken out the S1 variable and its corresponding coefficients. And then that's equal to the right-hand side as before. Once again, same idea. So now S1 is 0. So this whole term is gone. And we now have a 4 by 4 system of equations, 4 by 4 system of equations to solve for all the variables. So we do that, again, using whatever technique we feel like, and we get that J is 1250, X1 and X2 are both 50, and S2 is now 25. So we compare the J's, and this J is smaller than the J that corresponds to point A, so this is the optimal solution. X1 and X2 are both 50, so half the cars in each train will lead to the smallest cost. All right, so let's discuss the simplex method just a little bit more, kind of pull it all together, again, without getting into the details of the algorithm itself, because they do get quite complex. The first step is to put the problem into standard form. So remember, normally when we formulate these optimization problems, we'll have an objective function, we'll have a set of equality constraints, a set of inequality constraints, and positivity constraints. The standard form is after we've converted any inequality constraints into equality constraints using slack variables. There's also a few other subtle things, so we want to make sure it's a minimization problem. So if it is a maximization problem as posed, then we convert it into a minimization problem by just taking the negative of the objective function. Similarly, if we have greater than or equal to signs in the inequality constraints, then we want to convert those to less than or equal to, once again, just multiply both sides by -1 to flip the inequality. And then finally, introduce the slack variables to convert the inequality constraints into equality constraints. So once you've done all that, it's in standard form. Once it's in standard form, you can write down the simplex tableau of that standard form, as we just did for the train car example. And then we determine which of the variables are in the basic feasible, then we determine the basic feasible solution from the simplex algorithm, and that will help us get it started, basically. So let me say that a little more clearly. So remember, the feasible space is a polygon, so many-sided polygon. We know that the optimal solution is at one of the corners, and so what we do is we decide which one of those corners, which we call a basic feasible solution, which one we want to start the simplex algorithm at. And there's a whole bunch of details that go into that selection that we're not going to get into. From there, you just decide how are you going to proceed from one basic feasible solution to the next. So one corner or vertex of the polygon to the next one. So there's two keys to the algorithm, both of which we're not going to get into. And that is, how do you know where to start? And from where you start, how do you know which direction to go in order to, in the quickest way possible, determine the optimal solution? Basically, the second part is easy to conceptualize, at least, and you're going to go in the direction that's going to minimize J. So whichever one you start at with will have a certain J, and you want to go in the direction that will minimize the J, that'll make J smaller. All right, so we'll stop there for this video. In the next video, we'll do another example to see how this all comes together.